Pick any curve in the plane. Here, I've chosen a circle. Next, place a point on the curve and draw the tangent line to the curve at that point. Pick any arbitrary point, which we'll call the pedal point. Draw the line through this point perpendicular to the tangent. Now, plot the intersection of these two lines as the tangent line moves around the curve. This new curve, which is the locus of the intersection of the lines, is called the pedal curve, and all curves have their own infinite family of pedal curves dependent on the location of the pedal point. The pedal curve of a circle is a limousin, which I discussed in my previous video on roulettes. Pretty, isn't it? Okay, so we have a way to make curves from other curves. That's cool and all, but can we write a general formula for a given pedal curve? Yes, in fact we can. However, this will require some basic knowledge of calculus, especially derivatives. For simplicity's sake, let's say we have a pair of functions x of t and y of t, such that when used as the coordinates of a point in the plane, they trace out our curve. We say that these functions parameterize the curve. In calculus, you probably learned that the slope of the tangent line to some function f at x is the derivative of f in respect to x. So can we find the slope of the tangent to our parametric curve? Slope is change in y in respect to change in x. If we draw the secant line through 2 points located at parameter t and the other at parameter t plus delta t, it's pretty easy to find its slope. However, this is only an approximation. As delta t approaches 0, or as the 2 points get closer, this approximate slope gets closer and closer to the true value. In the limit, the finite differences in the slope formula become derivatives of x and y in respect to t, yielding our final expression for the slope of the tangent. From now on, I'll be using this dot over a function to represent its derivative in respect to t. It'll make our calculations a bit simpler from now on. But back to the original problem. We want to solve for the intersection of the tangent and perpendicular lines, so first we have to find their equations. Let's say that the pedal point has coordinates x0, y0. The equation of the tangent line in point-slope form is this, since we know that it's equal to the function for this given t value. The equation of the perpendicular in point-slope form is this. Note that the slope is the negative reciprocal of the tangent slope, which makes it perpendicular. Let's isolate the y's and set them equal. Now, we solve for x. This takes a little bit of algebra, which I'll do now in one smooth montage. I'm going to call the x-coordinate that we just found x sub p of t, expressing it as a function of the parameter t. The y-coordinate, y sub p of t, of the intersection point is the result of plugging in the x-coordinate of the intersection point, which we just derived, into one of the line equations. As you can see, I used the line through the pedal point. And with that, we found a pair of functions that parameterize the pedal curve, so we're done. Here's an ellipse. If the pedal point is in the center, we obtain a curve called a hippopede. If the pedal point is outside the ellipse, we obtain something like a stretched out limousin. Pedal curves of the cardioid are interesting as well. If the pedal point is on the cusp, the pointy part, we obtain a curve called Cayley's sextic. If it's to the left of the cusp, the result is a curve called Freeth's nephroid. Sticking to the theme of roulettes, deltoids have a multitude of interesting pedal curves. If the pedal point is in the center, we obtain a curve called a trifolium, or three-pedaled rose. If we move the point around inside the deltoid, we can obtain asymmetric versions of it. If the pedal point is on the deltoid, we obtain this two-lobed curve called a bifolium. If the pedal point is on one of the cusps, we obtain a curve resembling a flower petal, called a folium. Much like the deltoid, the pedal curve of the asteroid at its center is a quadrifolium, or four-pedaled rose. With the pedal point on the asteroid, we obtain this curve, which I call a bow tie. With the pedal point on one of the cusps, we obtain this linked curve, which I find quite pretty. The pedal curve of a hyperbola with the pedal point at the origin is a lemniscate of Bernoulli, a figure-8-like curve resembling the infinity symbol. Parabolas have a few interesting pedal curves. If the pedal point is on the vertex of the parabola, we obtain a curve called the cissoid of Diocles. If the pedal point is on the directrix of the parabola, we obtain a curve called a strophoid. If the pedal point is elsewhere, we obtain cubic curves called rational circular cubics, which I will now show a few examples of. I'm probably not going to make any more math videos for a while. I've put an interactive version on my website, linked below. So thanks for watching, and I hope you enjoyed it. Bye, and have a nice day.